Hi, everybody. Am I audible?
Yes.
Hello.
Hi. Okay. So let's start. Just the brief reminder that last time we talked mostly about still aspects of conformal field theories and conformal representation theory. We introduced this notion of radial quantization and then also the slightly unintuitive way of how to deal with conjugation and reflection. And we use that, however, to deduce some interesting bounds on the allowed dimensions, conformal dimensions of, let's say, healthy conformal field theories. So in particular, by looking at level 2 descendancy, we got what is called the unitarity bound. So not only is the conformal dimension of any operator in a unitary theory positive, but in fact it has a bound which is given by this expression in terms of the dimension. And as I said, this is the optimal bound and is saturated by the free scalar theory, as we have also established. And then just as an afterthought, although I didn't derive it, I gave you the case of the general spin L version of the unitarity bound. And those things are saturated by conserved spin L currents. But we're really now right there now in order to go to the goal, really main goal of the second part of these lectures, which is that we're going to use everything that we've learned essentially to discover anti-de Sitter and also to discover at least the low-lying, low-energy part of ADS-CFT duality. Okay, so what I'm going to do now is some sort of derivation of the dual relation. However, there is no, to the best of my knowledge, full derivation of ADS-CFT. That is still an open goal or a proof of this duality. And the problem is still to prove it all the way to the UV. So the whole thing, the duality that I'm going to work towards still is a conjecture, although one with an immense amount of evidence in favor of it. But as you can see, we can sort of constructively build up to it, at least in the low energy regime. And of course, you now know quite a bit about how to think about gravity in the low energy regime. And so I hope you will be able to benefit from that as we go on. But so let me give you sort of the general motivation where we're going. Okay, so what we're going to do now is basically we're going to work toward a geometrical representation of almost all of these statements that we made regarding the conformal algebra and conformal symmetry. So let me call this, yes, a geometrical representation. Okay. So recall that we basically have established some sort of triangle of conformal representations. So we started with what one might call the defining representation, or which we used as the defining representation, which was really in terms of d-dimensional vectors. Okay. So we were asking about the conformal isometries, if you wish, of R1 comma D minus 1. So these vectors are the conformal killing vectors of R1 comma D minus 1, which is after all a d-dimensional Lorentzian spacetime. So this is our representation here, right? So these were the things that we called, like, you know, x mu d mu for the dilatation, for example, and b dot x d mu, b dot xx mu d mu, and so on for the special conformal. You remember those expressions, basically the conformal killing isometries, conformal killing vectors of R1 comma D minus 1. So then, however, we related this to a second perspective, which is really the same perspective. Okay. So so obviously we said that, well, let me first write the second perspective. So we actually noticed that looking at the killing algebra acting on tensors, we found that this was actually precisely the same as the relations that you get if you look at the Lie group of SO2, D. And it didn't escape our attention that, in fact, of course, those things can also be realized as killing vectors, but they would be the killing vectors of some flat spacetime that is higher dimensional and that has a slightly funny signature. So those would be the killing vectors of R2, D. But at the same time, and actually, yes, no, I think chronologically it was this way. We also went from the defining representation. So again, remember, this is the same as when we talked about the Poincaré algebra as acting as isometries on Minkowski space. And then we looked at what are the unitary irreps of Poincaré. So the same here, we looked at the quantum manifestation. So if you want unitary irreps, but we represented this in terms of operators, right? These conformal fields on, if you want, the CFT Hilbert space. We didn't have some sort of direct relation between these, but I'll just draw the edge here of the triangle. And this whole thing, of course, I mean, all of these are, if you want, different perspective on conformal symmetry and theories that realize conformal symmetry, so CFTs. Okay. And so, however, there was something here, or there is something here in this corner, which I think can still be improved. And I would like to talk a little bit about that, okay? And once we've sharpened our view, if you want, on this representation, we're really almost all the way toward the why ADS plays such an important role in conformal field theories. So let's just notice that this R2, D itself. Okay, so here we had our R1, D minus 1. So this is an object that is not so different, okay? And in fact, it is just like R1, D minus 1. It is maximally symmetric. Okay, so let us ask the question: is this conformal algebra really all there is in terms of symmetries of R2, D? Right. So we know that our beloved conformal algebra here, it acts on R2, D as killing vectors, but is it really all there is in terms of killing vectors? And the answer is, I can anticipate, is no. But let's see how, for example, to work that out. Well, it is maximally symmetric, which means that it has actually, if we look at its equation for killing isometry, so this is equal to 0, okay? This actually has, this equation has a, let's say the equation has a certain number of independent solutions. So you can always say that for a maximally symmetric space in a certain number of dimensions. So it has a number of killing vector fields, which is equal to 1/2 d plus 2 d plus 3. Okay, I mean, I am being careful that this d is always the same, right? So here we have a d-dimensional space, here we have a 2 plus d-dimensional space, and a 2 plus d-dimensional maximally symmetric space happens to have this number of killing isometries. But we've also written down the dimension of the conformal algebra. So this was SO2, D. We've already written down that it has 1/2 d plus 2. That's promising, but actually it's d plus 1 here, okay? With the same d, obviously. And so what we conclude trivially is that the number of the killing vector fields, well, of R2, D minus the dimension of SO2, D gives us a mismatch, which is D plus 2. Which I just remark is the dimension of this spacetime, right? There is, this is a 2 plus D dimensional spacetime, so 2 plus D dimensions. So in fact, it's easy to immediately see what are the missing isometries there. The isometries are basically, this guy here is like the Lorentz group, right? It's just the rotations that rotate also the 2 time directions. So it's like the 2-time Lorentz group. But we know that this flat space also has the translations. And the translations are, of course, generated by a vector. And a vector in D plus 2 dimensions has D plus 2 entries. So what we have here is that the missing isometries are just the D plus 2 translation killing vectors of R2, D. Okay. And so, well, we could just, I mean, our conclusion, just to be complete here, is that SO2, D, which is the symmetry group appropriate for a D-dimensional CFT, is somehow, well, no, is in this precise way that we discovered a subgroup of SO2, D, which is Lorentz. I'll put it inverted commas because it has this strange signature, okay? And then it is the semi-direct product with translations, which have no, these translations have no analogs on the conformal field theory side. So then the question is, well, there's another hint, okay? So this was actually something that came up last week as a question. We discussed that a little bit. I mean, there's also one issue here that was immediately highlighted, which is that this is a D-dimensional story. And this is a D plus 2 dimensional story. So we increased the number of dimensions by 2. So let me tell you what would happen if we somehow managed to increase the number of dimensions only by 1. So if you say, so a maximally symmetric space in, so a maximally symmetric space in D plus 1, okay, this has a number of killing vector fields, which is actually 1/2 D plus 1, D plus 2, which agrees with the dimension of SO2, D. So this suggests that there is actually a manifold. So there is some manifold in D plus 1 dimensions, which realizes SO2, D as isometries. And no others. And of course, it won't surprise you very much that ADS in D plus 1 dimensions is precisely this manifold that we're looking for. But I would like to construct it now. I mean, we actually have all the hints in place of how to construct it. So what we want to do is we want to find some embedded manifold inside of R2, D, which preserves all of the Lorentz group, but which breaks all of the translations, right? Because then what happens is that we preserve all the SO2, D. Yeah, we have all it here. We preserve all the SO2, D, which is in fact the CFT thing. and we have none of the extraneous translations. So this can actually be done quite easily. So let's just look at a, so we will look at, we will construct a D plus one dimensional submanifold. D plus one dimensional submanifold of R 2, D. And let's say such that this SO2, D is preserved, but the translations, so let's call it P in 2, D. Sorry, that was P translations of 2, D are actually broken. And the way to do that is as follows. Okay, let's just write an embedding equation. So one equation, one constraint among the D plus 2 coordinates, which I will write as XA is equal to minus L squared. So L is some arbitrary parameter that enters in this. And this is an equation that you should read in R 2, D. And I used here the contraction with respect to this metric. So recall that we've written the metric in D plus 2 dimensions. This was the flat metric with 2 time-like directions as dxa dxb, and this was equal to minus dx0 squared plus all the effectively d spatial directions. So there's a plus sign, and then I had one more time-like direction. So when I talk about this contraction here, this contraction is minus x0 squared plus all the xi squareds minus xd plus 1 squared. And the whole thing is equal to minus L squared. That is the arbitrary parameter that I introduced. So it's a negative, this thing here is negative definite for L real. So, and the contraction, yes, the contraction here is obviously invariant under the rotation of all the x's. So that's SO2, D. But this equation itself is also obviously not invariant under the translations. Okay, I hope that's obvious to you. So it's sort of like a sphere. People like to call these things hyperspheres because they have time-like directions. But you can think of it as like a sphere in three-dimensional space. For example, x squared plus y squared plus z squared is equal to 1. And of course, then the sphere will define some special radius, and so translation is broken in this three-dimensional space. The same is true here. Okay, so, but now let us naively just pursue the properties, geometric properties of this space-time. Okay. I could, of course, just tell you this is ADS and then move on, but let's just work out the properties of ADS by staying with this embedding approach. So first thing is that this is a submanifold which has one fewer dimensions than R2, D. So we should choose a system of coordinates. So we should basically solve this embedding equation in terms of coordinates which are intrinsic to the submanifold, and that will then also allow us to write down a metric, or depending on our choice of coordinates, in fact, several metrics on this submanifold. So coordinates on ADS-D plus 1. I mean, yeah. Did I should really just, let me just call this already. This is ADS-D plus 1, okay? And ADS stands for anti-de Sitter. And the point of that name, of course, for those who don't know, is that if I had chosen here a positive sign, then I would actually end up with some space-time that is of relevance in cosmology, and that was for the very first time written down by De Sitter. And because you change the sign, you call it anti-De Sitter. Okay, so coordinates on ADS D+1. Would be kind of funny if someone now corrected me and said, no, there was actually a guy called anti-De Sitter, but I don't think that's historically accurate. So so one way of, so you want to find some coordinates which, if you plug them into this embedding constraint, it is just identically solved. And so one set of coordinates which people really like a lot is what's called global coordinates. But those will also be the first this will be the first set of coordinates that we're going to use. So I'm just going to write it down, and then we can stare at it and we can convince ourselves that it actually works. So x0 is L times cosine t over cosine rho. So t will play some sort of the role as time, and rho will play the role as some sort of radial direction. And by the way, again, just to tell you, in the familiar example, if you have the two sphere in 3 dimensions, then of course you're going to solve this embedding constraint by reducing it to 2 angles, right? So you're going to have, let's say, theta and phi. And so then you would write like the z direction is equal to the radius times sine theta sine phi, and then the y direction would be radius times sine theta cos phi, and then it would be cos theta would be the remaining direction, right? And that would solve the equation identically, and then theta and phi would be the coordinates on the sphere, and the metric would be the round metric on the sphere. And so we're doing exactly the same thing, just with this spacetime, which is a hypersphere in d+2 dimensions. So that's also maybe that's why it's not surprising that trigonometric functions feature. But because you have mixed signature, at some point you will also find, well, okay, let me not make too many comments. So xi is equal to L times the tan of this radial direction times, let's say, a selection of angles. I will define a little more what I mean by this. And then x d+1, so finally the second time direction will be L times sine t over cos rho. And the coordinates then are, we have basically t rho and omega I, which are d-1 angles. So that means that they satisfy something like omega, I guess I put a hat on them, omega I is equal to 1. What does that mean? Sorry, the sum, maybe I'll write the sum explicitly. I is equal to 1 up to d-1. So those parameterize a d-1 sphere of unit radius. So this is pretty much exactly the generalization to arbitrary dimensions of this story in 3 dimensions that I used as an analogy. So that story even plays a role in our actual embedding here. But now you can just convince yourself that those things satisfy the embedding constraints. So of course you're going to have to use the fact that these things square to 1. I have made a mistake. The mistake is that I should sum this to d, even though it's correct that is d-1 angles. Let me just, again, by going back to the 3D sphere example, I have 2 angles theta phi, but I have 3 coordinates that I'm writing in terms of those angles, because the embedding constraint will be x squared plus y squared plus z squared is equal to 1, but I can solve it in terms of 2 angles. And this is what I'm saying here, okay? Good. So So you're going to have to use the fact that these angles square to 1, and then just, adding squares of trigonometric functions, you can do that. And as you will be able to convince yourself, it solves identically this constraint. Good. So, however, this allows us immediately to find the metric. Okay, so the metric now is given as the induced metric. Okay, on ADS D+1, induced by this particular choice of solving the embedding constraint. So the point is, induced metric means that you restrict the flat metric, which was eta AB dxa dxb, to this pseudosphere xa is equal to minus L squared. So for example, the thing is just in practice, you will have to do things like dx0. Okay, now you of course have dt and d rho component here. So we'll have something like L minus sine t over cos rho dt. That's the t derivative. And then, no, cos rho, excuse me. And then you have the rho derivative, which will give you something like cosine t over cosine squared rho sine rho d rho. And you do the same for all the other coordinates. You plug it into the flat metric, and what you find is, after some simplifications using trigonometric identities, you get L squared divided by cosine squared rho times minus dt squared plus d rho squared plus sine squared rho d omega I d omega I. And that is a equation that I wanted to put in a box. And this is a coordinate system that people like to refer to as global coordinates. On ADS-D plus 1, roughly speaking, because it's an example of a set of coordinates which covers the entire submanifold that we're interested in. There are also other choices of coordinates which only cover so let's say half of it, for example, one half or the other. All right, so what I would like to do next is I would like to tell you about how to think of this, the boundary of this space, because this holographic correspondence, as you may have heard, is going to also have an important ingredient, is going to understand the boundary. But before doing so, let me make one remark. So of course now we have the LAB. They act as isometries on R2, D trivially, right? So we have something like LAB or equal to XA dB minus XBDA. Okay, these are just the standard Lorentz generators. And then we can now use the same embedding constraint, or just let me just say use our embedding to work out their action on ADS-D plus 1. Right, you do the same thing. Remember, we just did, for example, dx0 Okay, this became an expression in terms of dt and d rho. So obviously d by dx0 will become some expression in terms of derivatives with respect to the coordinates. And so this is a way of constructing, this constructs the, this will result in the killing vectors and all of them. Okay, actually let me say all killing vectors or all killing vector fields of ADS d plus 1, which is going to be, again, our conformal algebra. And we will return to this later on. But yes, I just wanted to point out that it's easy now, or, algorithmic anyway, there's a bit of calculation there, to get precisely how does the conformal algebra act on this space. And by construction, also, these are going to be isometries and the exhaustive list of isometries of this space. I hope that's clear. Okay. So MEG, well, let me just mention one of them. The time translation killing vector field of ADS d plus 1 is algebraically the same as the dilatation operator in CFTD. Now I said algebraically the same, meaning that it has the it falls into the place of the generator that we already identified with the dilatation. But what we're going to do maybe later today, otherwise next week, is that we're actually going to show that you can precisely identify this killing vector field with precisely the dilatation operator of a CFT if we identify that CFT as being in some sense defined on the boundary as we take the limit of the space-time to the boundary. But I'm just anticipating something that we're going to do in detail. So there will be a precise duality map between the isometries as we establish them now and the conformal algebra of the CFT that is going to be the CFT that is dual to this ADS. Already using that language now. Okay, so good. So now, but that was just again a little bit of well, maybe preview in fact of algebraic aspects. But I would like to continue with the geometry. So now I would like to look at the conformal compactification of ADS-D plus 1. Okay, so this is a new heading. And the reason why we do this is that it is necessary in this case to understand the boundary of ADS-D plus 1 in a sense that will become clear. I do sort of expect that there are quite a few among you who know about conformal compactifications and in particular the example of Minkowski space, but I will still go again through how it works from Minkowski space, both as a reminder, or for those among you for whom it is new, also as a first introduction to the idea of conformal compactification, but it also, that precise structure that we're going to work out will play a prominent role even when we go to ADS. And the good news, by the way, is that actually conformal compactification of ADS is much easier than of flat space, especially since we've already chosen a way of looking at ADS in which this can be done very efficiently. So let's go to flat space. So what is this conformal compactification? Well, it's basically just, it's a useful representation of a space-time and what does it do? Well, it brings the notion of infinity of a space-time that bring, always get two of these reminders, that brings infinity, so the idea of, you know, points that are infinitely in the at infinite distance, to a finite locus, let's say, and that preserves the causal structure. So it preserves, locally preserves the light cones. It doesn't preserve much else. So this is quite a, I mean, this is quite a violent thing to do to a space-time, but it preserves the causal structure. So in particular, you can immediately see what happens to light rays, okay? And it brings the whole infinite thing to a finite representation. And in particular, this is useful, as I already mentioned, to understand the boundary of ADS D+1. Okay, so let's do the Penrose diagram of flat space. So this is mostly a reminder. Penrose diagram is just another name for the graphical representation of the conformal compactification. So we have the metric ds squared, which is equal to minus dt squared plus dr squared plus r squared d omega d minus 2 all squared. Okay, so now this is flat space, and we are in how many dimensions? D minus 2, D minus 1, D. So this is D-dimensional flat space. So we would say that this is R1, comma D minus 1. Okay, and I've chosen, well, I've chosen this dimension for a reason. So we have minus infinity is less than t is less than infinity. I guess I should say less. Okay, and we have the radial direction. So I've written it in a way that I have a radial direction which itself is positive 0 less than r less than infinity. And then of course we have our angles on this d minus 2 sphere. However, the d minus 2 sphere will not play a role. In some sense, we do a symmetry reduction. So we're really going to focus on our attention of what happens in the dr plane, where every point on top of this dr plane will be a d minus 2 sphere. But that will become clear anyway. So because all the action is in the t minus r plane, so let's start by bringing things to a finite distance. So define well, I define two variables, u and v. So twice u is t plus r, so the one of the light cone directions, and v is t minus r, which is the other light cone direction if you want. And then, of course, the whole infinite Minkowski space is covered in the range minus pi over 2 less than or equal u v less than or equal pi over 2. That's just the magic of the tan function if you want. And the metric, after a small computation, it becomes 4 du dv divided by cosine squared u cosine squared v. Okay, there's two things that are obvious here. One is that these are light cone directions. So whenever you have light cone directions, then the whole minus dt squared plus spatial direction becomes just a product of the two light cone directions. And then because they are also rescaled by this tan, you have some non-trivial, let's say, warp factor here. And then plus, okay, the r direction, the radius is just tan u minus tan v all squared times the sphere, omega d minus 2 squared. That's just, again, a simple change of coordinates. But maybe we note that this has, let's have a warning sign here already. In red, there are poles at u is equal to pi over 2 and v is equal to pi over 2. However, this is really not to worry in many ways, but one way in which it's kind of logical to see these poles here is that what we've done is we've put infinity to a finite distance, but you know, you pay a price because tan u, I mean, the point is that it diverges as u goes to pi over 2, for example. That's the whole point. And this divergence, which allowed us to bring things to a finite distance, but it rears its head by introducing this singularity here. But not to worry, because the point is that we only are interested in causal structure. Okay, only interest in some sense, interest in causal structure. And if this is your goal, then you can just allow yourself to do a Weil transformation to remove this prefactor. This is a bit of a formal thing, but right, you can convince yourself that a Weil transformation preserves the causal structure, it preserves local light cones. And if all you're interested is to have things at a finite distance and preserve the light cones, then you can just you know, get rid of such factors by doing a Weil transformation. You can do Weil transformation to remove the poles. Okay, but let me remind you again, this is not some physical symmetry. I mean, in no way this is some physical symmetry. I mean, this is just a geometrical thing that we're doing to get a representation of the original spacetime, which is useful. Okay, so this is not going to be equivalent to the original spacetime, nor is it somehow the application of some symmetry. It's just that we're massaging the metric in such a way that we get a useful representation. And this useful representation is the conformal diagram. So then, just doing this, so I multiply by cosine squared u, cosine squared v, but I do have to do it consistently. I have to multiply the whole metric. So I also have to multiply this bit by cosine squared u, cosine squared v. I get minus 4 du dv. I've gotten rid of it. And then I get some factor which, when the dust settles, is actually equal to sine squared u minus v times d omega d minus 2 all squared. Which now I'll do one final transformation. You see, as I sort of anticipated already in flat space, this is a little bit complicated, but it is customary to write this instead as minus dt squared plus dr squared plus sine squared r d omega d minus 2 squared. So what has happened here? Well, not much actually, because all I've done is, whoops, I've basically gone from the light cone UV to non-light cone. I can't put it there, sorry, because it's so low on the page. Some of the features of this app don't work. I would like to put a box around it, but I can't. But anyway, all I've done is I've basically defined t is equal to u plus v, and r is equal to u minus v, and then I get this final form of the metric. And so now let me draw the resulting diagram, and then it will be a good time to pause. Actually, maybe I can copy, paste. And I might even be able to put a box around it here. That would be nice. Okay, so and so we often draw this. We basically now have a t and r direction, right? So the nice thing is now that this is sort of like a compactified time, and this is a compactified radius. So they are in some sense morally quite similar to the time little t and little r the radius that we started off with. That is the sort of one of the main motivations to go to this. So these are the axes. And then our space-time, well, it's going to be actually going to be this triangle here. It is aligned like this. Basically the coordinate ranges are minus pi. If you just trace through again the changes of coordinates that we've done, it's less than pi, and 0 is less than or equal to r is less than or equal to pi. I should say that I've basically gone to d greater than 2. The two-dimensional Minkowski space, well, maybe I'll give a little drawing of the two-dimensional one, but what I'm doing here is only true strictly for d greater than 2. And so what we have is basically we suppress the angles here, right? So every point on this diagram, every point is really a d-2 sphere on top, right? So if I had a point here, this would be some point in the TR plane, and there would be a sphere of size sine squared r here on top of it. So now, what we can do is we can draw constant r slices of constant r. So the r is equal to 0 slice is the one here. And then if I increase r, I start foliating this thing in such a way that I approach the asymptotes here. Okay. And then there are the constant t slices. Sorry, these are constant. I mean, I said it, but I should have said these are constant little r, okay, slices. We know what constant big R slices are. And then we have the constant little t slices, which look a little bit like this. Okay, and so these are constant t slices. And then let me just write down some names before we go to the break. So this thing here, this is time-like future infinity, which people like to call scri plus. So it's some sort of curly I. Then this is time-like past infinity I minus. This thing here is what people call, this point here, space-like infinity. This is I0. So here just R goes to infinity, whereas here R and T both go into, here just R goes to infinity, and here both R and T go to infinity in some way. Here into the future, here into the past. And then, of course, we have the origin 0 here. Let me just make sure that I'm just putting on those names for completeness, okay? This is really not important for this course. I just wanted to put it on for completeness because I drew the diagram. What's important, so let me draw it to a conclusion here, is that we did all these transformations in such a way that all of Minkowski space now is this little finite set in the capital T, capital R plane, and that what we would have thought, well, what is physically infinitely far in the future are now brought to this segment, and that point. Okay, so it's immediately visible. And we've done it in such a way that light rays still go at 45-degree angles in this diagram. This is, of course, important. Okay, light rays will still go at 45-degree angles in this diagram. And the last thing I will say is that on the way, what we had to do is we had to get rid of some poles, which we did by Weil rescaling, which is purely a device of convenience for now. Okay, so good. I think I'll leave it here. I might just say, okay, I was telling you in d is equal to 2, people basically draw the diagram like that. And you have, you know, these slices here that go like that. And why that is, you can ask me in private if you want, but I just wanted to tell you that because sometimes people get confused. So this is the generic case, and in 2 dimensions, you have this slightly special case. Okay, so are there any questions? It doesn't appear to be the case, so let's meet in 10 minutes at 11:15 on the other link, and let's immediately go to doing this in ADS, which, as I promised, will actually be much easier. Okay, see you in a few minutes. Bye-bye.
Bye.
Right, so let's continue. So we've now done the slightly painful work of understanding or reminding ourselves of how the conformal compactification, aka the Penrose diagram, finding the Carter-Penrose diagram of flat space works. And now let's do the same thing for ADS. And really the good news is that this is going to be much easier. So conceptually, of course, it's the same thing, not easier, but in practice, we basically don't have to do anything because we're already in a shape where the coordinate system is very much adapted to what we want to do. Okay, so on to ADS D+1. So again, just as a reminder, we have done our 1, D-1, so d-dimensional Minkowski. Now we're going to do D+1 dimensional ADS. So on to ADS D+1. So we have the metric, I remind you, of L squared over cosine squared rho times minus dt squared plus d rho squared plus sine squared rho d omega d minus 1 squared. So there is this d minus 1 sphere there, and if I'm not entirely mistaken, this is the correct dimensionality. And just as a remark, this thing that's inside here is what people like to call the Einstein static universe for historical reasons. Actually, amusing comment, it is because Einstein wrote it down, and remember that Einstein had written down the correct form of the universe with the positive cosmological constant, and then basically castigated himself by saying it was a really stupid thing, is a lie that he had done, and he developed another version of the universe, which was in fact in the end incorrect, and that's this Einstein static universe. But what you can see here is that the way that we wrote the metric is already of this form, that it has some kind of factor here ahead with a pole, and moreover, I don't know if I wrote this. I think I did. I hope I did. The coordinate rho already is compact here. So rho is already runs between 0 and pi over 2 in this. So this has this already has if you want the singular Weil factor, which is L squared over cosine squared rho. Of course, the important part is just the cosine squared rho, which has a pole as rho goes to pi over 2. So all we need to do is now do the Weil rescaling. And we end up with the metric ds squared is equal to minus dt squared plus d rho squared plus sine squared rho d omega d minus 1 squared. In other words, the Einstein static universe isolated. So two remarks here. So that I basically swept a couple of things under the rug, but one of them is that, so we didn't have to bring the radial distance, which is the one that gives us actually the distance to the boundary, to finite distance, because I'd already chosen a set of coordinates where rho had a finite range. Okay, there are a lot of people that actually prefer, well, not a lot of people, there's just a lot of literature which uses a system of coordinates which is global, but which has a radial coordinate that has an infinite range. That's also a very convenient set of coordinates for many calculations, but here I've already chosen it immediately such that we get a compact coordinate range. But however, the time direction is not compact, and we just choose it now to leave it non-compact, and you will see why. It doesn't really make much difference for our application, but if one wanted to, of course, one could also go to a compact time direction. But this is the usual way that people go about doing this in anti-de Sitter space. And so the conformally compactified metric that we end up with, where compactified should be in inverted commas because it's really only the radial direction that has been compactified. But anyway, that metric is here, and it's the Einstein static universe. The point is that it looks a lot like flat space. Well, what have I said here? Well, yes, it looks a lot like R 1, D. But has different coordinate ranges. Okay, what do I mean by that? So look at, yes, look, it's basically this metric here, right? Of course, I've changed the dimensions slightly by 1. So this d-2 sphere here is a d-1 sphere there, but the structure of the metric is exactly the same. So it looks like it is R, it looks like it's exactly R1, D, but it's not correct because the coordinate ranges are different. So the difference here is that we have 0 is less than rho is less than pi over 2. So the radial direction previously that we called capital R ran all the way to pi. And then we have minus infinity less than t less than infinity. And so a way of drawing it is actually, so we draw the two, we draw the time direction, which is infinite in both directions. Okay, goes on like this. And then we have our radial direction rho, which goes from, let's say, so this is t, and this goes from 0 to pi over 2. So there is the rho is equal to pi over 2 here. And this is what I would call, the boundary. But this is what everybody calls the boundary. So each point here, so each point on this manifold has an S d-1. Okay, this is just this sphere here. What I wanted to point out is that the boundary is, so you see, the boundary is of course exactly where this guy was singular, so we should take note of that. But now, simpler remark, the boundary therefore is obtained in this metric where I've gotten rid of the singularity, evaluated at pi over 2, where this sine squared is just equal to 1. And so the boundary metric is just minus dt squared plus d omega d-1 squared. So it's of the form, okay, the boundary here is of the form a factor of the real line for time times just this d-1 sphere. Okay, this is that d-1 sphere here. And the metric, again, is now, the metric is easy to read off. We just set the sine squared to be equal to 1. And so there, the boundary is, of course, at fixed rho, so there is no d rho term. So it's minus dt squared plus d omega d-1. And this is this famous statement, which either you've already heard a lot, or you, if you read the ADS-CFT literature from now on, you will see a lot, that global ADS has a boundary which is topologically R times a sphere, R times SD minus 1, okay? And then also what one often sees is that the topology of R times SD minus 1 is referred to as the cylinder, because you have like a time direction, then every slice is a sphere. So in the simplest case, it would be a one sphere, and then would be literally a cylinder. Okay, so so as I said, it's not quite a finite diagram, but it is enough for our purposes, and it's not finite because we didn't bother about the time direction. But you know, we're okay with understanding what this time direction means. However, now there is a big difference to what we had in Minkowski space, and that's worth highlighting. Namely, there's a time-like boundary of the shape R times S d minus 1 at rho is equal to pi over 2. And this is what we refer to as the conformal boundary of ADS. This is always what we really refer to when we talk about go to the boundary, or this and that quantity is defined on the boundary, and so on and so forth. But it's time-like, okay? And you see, we can actually immediately see that it's time-like because our conformal diagram, it still satisfies the property that it preserves the causal structure. So light rays still go at 45-degree angles. And what we see here is that this is a vertical line. The boundary is a vertical line, which means that it's time-like, okay? In Minkowski space, remember, there was not a time-like boundary. The boundary, well, the asymptotic boundary, okay, was null. It was itself a 45-degree line. It was a constant u or a constant v line in our coordinates. So there is this big difference that the boundary here is the is time-like, whereas it's null. Did I say time-like? The boundary here is null. Okay, it's light-like, null. In Minkowski, the asymptotic boundary is null, 45-degree angles, whereas it's time-like in ADS. And just as a remark, okay, this of course is not a boundary because it's just the origin of the radial coordinate. So this is just like the interior, but it's perfectly regular locus because it's just the origin of the radius. And the same remark is true here. This is just the origin of the rho coordinate. So it's just the interior, okay? Sort of like a polar coordinate system with some radius, but that doesn't mean that there's a boundary. It's just the center, okay? So there's a boundary here, but here the boundary is time-like. It's a vertical line, not 45 degrees or not horizontal, okay? So there's a time-like boundary. And then if you study the geodesic equation, which I think is on the 4th problem set, you can convince yourself that null rays, for example, reach this boundary in finite time. Okay, so yeah. And so that both of these remarks are basically pointing to what the fact that this boundary plays a much more important role in the study of ADS than the asymptotic scry plus and scry minus play in Minkowski. So in Minkowski, you can just sort of radiate things away and they will just go off to infinity and you never have to think of them again. More or less, that's what we think the story is. In anti-de Sitter, you can't do that because those things bounce back, right? So what it means that those things come back in finite time is that you could send out a light ray here, and then sooner or later you'll see it again. It'll come back. So if you want to understand what happens at this point, that, okay, by coincidence, actually I conveniently put here, if you actually want to know what happens at this point, then you also need to understand what happens at the boundary. So what precisely is the boundary condition, and so on and so forth. Okay. So the boundary plays an extremely important role in the dynamics of ADS. That's just a classical statement here about the causal structure of ADS. But it is also a fundamental ingredient in this ADS-CFT duality, because you see, what we're going to do is we're going to say eventually that the whole dynamics of the ADS are somehow dual to the dynamics of a conformal field theory on the boundary. And the fact that the conformal field theory can affect what's happening in the interior is very, very much tied to the fact that you need to specify boundary conditions even to understand anything that happens in ADS, just in principle. Okay. Good. So just maybe to throw out that word here, from a classical perspective, if I just asked about classically, how do you describe the wave equation, for example, on ADS? These properties here, one would refer to them as saying that ADS d+1 is not globally hyperbolic. Meaning it is not the future development of a Cauchy surface. But okay, we'll get back to maybe that nomenclature, but it's just useful to have heard this. Okay. So in other words, it's not just enough to specify initial data, you actually also have to specify boundary conditions. Otherwise, things are not well defined. Okay, so now let me give you just a little bit maybe of a geometric intuition about this diagram. So we had our rho is equal to 0 origin, and we had our rho is equal to pi over 2 boundary. And so we can think about, just for fun, two kinds of geodesics. We can think of one geodesic which basically orbits the origin, okay, and that would look like that, would come in, and then it would have these sort of bounces off here. So this is just like a radial orbiting geodesic. Okay. And sorry, it's just a radial geodesic, to be distinguished from one that, say, has some angular momentum that can be orbiting, and that could stay in this diagram at just some finite rho. So this would be something like a non-zero angular momentum orbiting geodesic. But this is not very intuitive from this diagram, and so what I wanted to tell you is how you can think of this in a slightly more geometric way, and that's if we draw this cylinder. Okay, so what we can do is we can draw our ADS now. So this is just meant to be helpful, okay? This is not some exact transformation now of this picture where I'm writing down some coordinate transformations, but it is an obvious, useful way of thinking about ADS. So we sort of, we have here now some different picture in which we include some of the angular dependence. Okay, so what we have is we basically still have rho now, but rho is really the radial direction. Okay, so and there is now some angle also that we might call theta. Okay, the angle around this direction. And rho is equal to pi over 2, meaning the mantle of the cylinder. Okay, that would be the boundary, and the solid cylinder on the inside is the interior of ADS. And so the center of ADS is literally going to be the axis of the cylinder. It's not a very straight axis, sorry. And so now time still goes upwards. And now this radial geodesic, what it would do is, it basically oscillates back and forth from some maximal radius through the origin to another maximal radius. And so it looks in this picture like so, right? It just spirals its way up in time. Okay, but it's like an oscillation around some maximum radius okay, which you see here, just oscillates back and forth about some maximum radius. I mean, I didn't actually mean this for this radius to decrease. Okay, this is just a limitation of my drawing here. Or no, sorry, I think I showed you the wrong geodesic, right? Sorry. So I'm going to just draw the different color over it. So what I have here is one that stays at constant radius, but goes forward in time. Okay. I apologize for this. So this is the blue geodesic. That really is this geodesic, because what's happening is that, as I was trying to say, is that this thing has angular momentum, so it orbits, and because it orbits, it's able to stay at constant radius. And so what it does on this diagram is just it spirals. Okay. Right. Sorry. Is that clear? I hope, sorry, I messed that up a bit, but I hope that's clear.
It is.
Yeah. So, and this picture here is sometimes people call that the tin can picture of ADS, just because it's like a soup can or something. And the point is that it's really the solid cylinder. Okay, so if you have like your soup can, like the soup is the whole of ADS, and then the mantle on the outside is the boundary, and the boundary is here also recognizably of the form R times SD minus 1. Okay, so but now so much for the compactification. Now I would like to talk a little bit more about how we define actually the boundary of ADS. So we've said that the boundary of ADS is what is situated at rho is equal to pi over 2. But in actual fact, now we have to confront the fact that the ADS metric before the Weil rescaling had these poles here. Okay, and so these poles actually will introduce a subtlety regarding the definition of what is really the boundary. And so I would like to address that subtlety now, and that will also give us a clean definition of what is the boundary and what's the metric on the boundary of ADS, which is something that we will have to use frequently in what follows. Boundary of ADS-T plus 1. So the simple remark here was that our original metric, the line element, will go to infinity as rho goes to pi over 2. That's because of this pole. And so to define a boundary metric, so we have already done one of them, but to define a boundary metric, all that we needed to do was to rescale it in such a way that this pole disappeared. We rescale, in other words, such that we have some metric that I call G bar now, which is of the form rho minus pi over 2 squared times G ADS. So what I've done is precisely gotten rid of this is precisely cancels precisely the pole and just the pole. Cancels the pole. Okay, there's a double pole here. You had, well, I can write it 1 over cosine squared rho, which near pi over 2, just cosine goes like rho minus pi over 2. So this has a double pole rho minus pi over 2 all squared. So we've now defined this auxiliary thing G bar. And then the boundary metric, as we have done really, then G boundary. So this is now the metric just restricted to the boundary, which therefore depends only on time and these angular directions, omega I. This is what we would call the limit of rho goes to pi over 2 of G bar. So we've done one such thing where we basically just multiplied it by cosine squared. And then the limit is finite, and we were able to extract this limit. And this limit was what I called r times sd minus 1. But as I was pointing out, or as I'm pointing out here now, is that this is not unique. So this procedure is not unique. Okay, because all that really counted was that I have some function which near pi over 2 has, well, which at pi over 2 has this pole. Okay, so the only requirement is to cancel the well, sorry, 1 over rho minus pi over 2 pole, double pole. So for example, okay, equally valid, you could have had g bar primed, which is equal to any function, in fact, of t and the angles times rho minus pi over 2 squared GADS. So any function that at pi over 2 has this double zero, so this is multiplying, okay? So this function depends on the arguments, everything but the radial direction, and then I'm multiplying it by this double zero. Okay, this is the structure that I'm writing here. So this is equally valid because it eliminates this double pole, but it gives you a different boundary metric because its boundary metric is, well, you're seeing it already, but this G primed boundary, this is of course equal to f of t omega I times G boundary. And of course, you know, I hope that was clear, but this function f, I mean, it should be positive, definite. Why is that? Because you don't want to change the signature. Okay, we don't allow ourselves to change the signature. We'd be not doing ourselves any favors by changing the signature. But otherwise, this is just any positive definite function. And so this is precisely, let me copy paste again to the next page. Okay, this guy here is precisely what we would have called a Weil rescaling. So, so tentatively, what we say is that the boundary metric is defined only up to Weil rescaling. Okay, and actually, this is something that is a well-known situation in say, differential geometry, and in this context is referred to as a conformal class, if you want, of metrics. Okay, and so in the sense that G prime boundary and G boundary, okay, they are in the same conformal class. They are but two representatives in this class. So what we have, for example, we have here, just to put a little bit more of meat on this, we have the G boundary. We had G boundary. We have already established that this was r times s d minus 1, which we can actually write as some rescaling, in fact, of rd. Okay, we will see precisely what that rescaling is. Well, let me just make that remark, or we could have also said r1 comma d minus 1. Okay, so the difference is that either I'm in Minkowskian signature when I have rd, or I'm in Lorentzian signature, which is actually the signature that we've mostly worked with, in which case you have r1 comma d minus 1. So what I'm telling you is that it is very natural to think of the boundary of ADS as being r times sd minus 1. But in fact, it is equally natural you can find some rescaling, so some alternative function f here, such that if we went through the same procedure before, we would have actually discovered that the boundary is not r times sd minus 1, but just d-dimensional Minkowski space, so flat space. Okay, and this is just one other example of a way of thinking about the boundary of ADS, but it's one example that is extremely popular. So both of these examples, r times sd minus 1 and r1 comma d minus 1, are very popular, and there is a particular conformal rescaling or Weil rescaling between them, which we will get back to. I don't want to go into now precisely what is that function, but we will go into it in the not too distant future. But the important point that we need to drive home is that ADS does not have a boundary metric. Instead, ADS has a conformal class on the boundary, and any representative of the conformal class is just as good as the other. However, there are certain choices that are convenient, either because, well, they will be convenient because we like to study properties of the boundary in this form, or properties of the boundary in that form, or in some sense they're natural because they're kind of canonical examples, if you see what I mean. I mean, the first thing that we saw was a particularly easy way of solving this embedding constraint. So in some sense, this is preferred in one way. But there is no, okay, but there is no mathematical uniqueness to any of these choices. Okay, and this is going to be, again, is going to be crucial for what we're going to do in this ADS-CFT duality, because this property also allows us, in fact, to show that the isometries of ADS-D plus 1 become conformal isometries of the boundary. Because remember, to have conformal isometries, the boundary metric had to be related in some sense to omega squared times the boundary. This was the defining equation from which we got this whole conformal isometry and conformal killing vector idea and so on. And the fact that the metric is really only defined up to such a rescaling turns out to be crucial for ADS-CFT to work. Okay. Right. So that is really all I have to say on the geometry of ADS. And we also talked a bit about the geometry of flat space. And I'd like to move on to now relating the various representations that we've talked about. But there is certainly time for some questions now, if there are any. Okay, seems like everything is clear to you. So let's move on to relating the various representations. And now, as you can see, we're getting closer and closer to building this idea of duality. So there is one question. Okay, let me just write this. Yep, go ahead, Adrian.
Hi, Julian. So I was getting confused again at the usual thing about conformal invariance and Weil invariance.
Yeah.
Because with this comment about the boundary metric, we seem to be pointing towards the claim that the boundary theory is going to be Weil invariant instead of conformal invariant, right?
We're not heading toward that claim. So the point is that it will be invariant if that Weil factor is one of the ones that are allowed by our conformal transformations, but the theory need not be invariant if that factor omega squared is a general Weil transformation. That was, and how that works, I mean, I won't have time to actually go into the details here, because for that you need to understand in detail what's known as holographic renormalization. But there are some very nice papers which explain that. And the key word here is the so-called holographic Weil anomaly.
Okay.
So you can actually show that if you do a general Weil transformation, then in principle, the two boundary theories will not be the same. There is going to be some anomalous contribution, as has to be the case. So just to, again, to give you a concise answer, which I think I gave in the beginning, no. What we said does not imply that the boundary is Weil invariant. It does not.
Okay. Okay, thank you.
Okay. But I mean, it's still an important point. The answer to really work out how that works is subtle. And it has to do with the fact that there are some infinities in the game here. And those infinities can actually be treated in exactly the same way as you do in the renormalization group. And again, there is a relationship between the Weil anomaly and the renormalization group, which maybe some of you know, but that's how it works.
Mm-hmm. Okay.
So, good. So, so this is basically towards building a duality between ADS D+1 and the D-dimensional CFT. And we're already working now towards the notion that in some very strict sense that the CFT is going to be on the boundary, and the theory on ADS lives on the entire ADS space. Okay, actually, I mean, in a more modern parlance, I do want to make that disclaimer, I'm sorry. This is not entirely correct. We really should think of the CFT to be related to the ADS at every radius, but how this relation works, again, is related to the idea of renormalization group, and I may or may not have time to go into that. Okay, so for the time being, it's most useful to think of it as being really at the boundary. So the first steps we will take in this direction is, A, we will show that the isometries of ADS become the conformal isometries of the boundary of ADS. And the second one, which is the one that is more non-trivial in some sense, we say that if we define some effective field theory in ADS, some QFT in ADS, then some bulk operator phi, some field that lives on ADS, can be associated, in a precise way. There's going to be a map to an operator in this conformal field theory which lives on the boundary. So here we have a bulk field, but it's a quantum field, so I mean it's also an operator, right? And this is a boundary CFT operator in precisely the way that we talked about CFT operators in the last couple of weeks. And the second part is sort of like a major part of what people call the ADS CFT dictionary. So it allows you to translate from certain bulk quantities to certain boundary quantities. And in fact, there is also an opposite direction, but let's not get into that now. The final remark is that the way that I'm going to be able to establish this is by thinking of what happens in ADS as an effective theory, including effective theory of gravity. So that also justifies why I spent quite a bit of time, I mean, quite apart from its intrinsic interest, but quite a bit of time talking about effective field theory of gravity. But secondly, it also explains my previous remark, which is that the way that I can sort of really constructively establish this duality is only going to be true in the low energy limit. But the major advantage of this ADS approach, rather than the flat space, is that I can also tell you how the UV works, okay? And I will get to that hopefully by the end of this lecture course. But before we go into these lofty topics, let's go and do something very down to earth. Let's make a crack at this point A. So this is now, let's look at bulk isometries, induced boundary conformal transformations. So let's work in this global chart. Okay, let's say global, and we have T, rho, and then we have our angles. So I'm just saying theta and other angles, or you could call it theta 1 and other angles. Right, so the correct interpretation, well, not the correct, D, the dilatation operator is minus d by dt, okay? So this is, by the way, this is the thing that I told you earlier. You can just have this descent of the isometries of R2, D to the pseudosphere, which is ADSD plus 1, using the embedding constraint. And that will give you, among others, the following relationships. So the dilatation operator is d by dt. The momentum operator is omega I minus sine rho ddt plus I cosine rho d rho plus some angular bits that I don't really care about in this derivation. So let me call them theta I. We don't need them here, okay? These are some angular bits which are not needed in this analysis. Basically because they disappear in the boundary limit, okay? And so we don't need to like carry around things which anyway go away. And then we have that Ki is going to be equal to minus this expression for Pi star. And finally, we also would have our J generators, but they're also not relevant for the argument that we have here because I'm going to only look at, obviously, a scalar field. So let me take the boundary limit, okay? And so let me say that there's this claim. Well, no, let me make the claim. Namely that the limit of rho going to the boundary, which is pi over 2, of this whole bunch of things, d, pi, ki, and actually also the j's as ADS isometries. Okay, this will precisely give me, well, I'm just going to write the same guys, but now they're not ADS isometries. Now there are conformal isometries of RD, which I want to identify as the ADS boundary, okay, in some correct coordinate system. So I'm sorry that I started talking about Euclidean signature now, which explains why I called these I's. And that's just a little bit more convenient right now. But the other thing that I did, and this is where we find, by the way, this correct Weil rescaling, is I'm going to work with a representation of the boundary where the boundary of ADS is RD. And by the way, just to maybe ease Adrian's worry here a little bit, the relationship that takes us from RD to R times S D minus 1 is actually a conformal rescaling, not a general Weil rescaling. This is actually a proper conformal rescaling. Okay, so this one, for example, is just allowed. Okay, so let me just do the D one because we're already kind of over time. Okay, so I will, yes, let me just do D. So what we have is, so this, okay, the slightly sad thing is that this one seems like it's awfully trivial. The P1 is actually not so trivial, and it sort of illustrates more what's going on, but I just don't have the time to do this now. I'll probably just write it on the notes here before I upload them on Moodle, and then you can see for yourselves. But let me just do D. So D on RD, we can of course write this as, you remember all these things. This is xi d by dxi, but these are now really the boundary directions, okay? Boundary directions xi. Well, we were able to write this in terms of the radial time as I d by d tau, okay? Which is minus d by dt, where t is I tau. And that's going from Euclidean to, from Lorentzian to Euclidean signature. And this, of course, is now the limit. Rho goes to pi over 2 of d ADS. Okay, because d ADS was just, I stated to you that if you look at our identification, you find that it's minus d by dt. So why am I a bit annoyed that now I'm time limited to do this? Well, the only non-trivial thing that has gone on is somehow juggling a bit with the signature and changing coordinates on the boundary itself. The limit rho goes to pi over 2 was totally trivial because nothing depended on rho here, right? I'm sorry, that's how it is with the dilatation operator. As you can see, this will not be the case if I were to look at the p operator. So there, it would be non-trivial that you have a well-defined limit as rho goes to pi over 2. But let me just write this out in a hopefully neat way, and then you can look at it for yourself on Moodle, because we're really already over time. But the point is that my claim is that basically for all these generators, you can find that the boundary limits precisely give you the conformal isometries of the conformal boundary metric, the representation of the conformal class of the boundary that gives you the metric on RD or R1 E minus 1. So in some sense, sorry, this was all a bit rushed now, but in some sense, this establishes step A. But okay, I haven't given you too many details, but I will give you at least the one row dependent case, and that should be a better illustration. So let's leave it here, and let's take up next week where we basically go to step B. Okay, but as a homework, please also go through in detail through the R dependent example that I will put in the notes on Moodle. That would be important. Okay, so far so good. Any questions? Well, I have a question, by the way, for you. I mean, there is slightly more material than I can cover, I think, in 2 hours next week. So one option would be I can compress it and again, basically give you more of the details on Moodle and you can look at it yourselves. Another option would be that, let's say next week we just do a slight marathon in the sense that we do, say, 3 sessions rather than 2. I think 3 sessions would give me more time to at least go more into detail on some of the more salient features. Would people be okay with that?
Yeah, for me it's fine. But
okay, so
you would like to start before or to end later?
This I'm not sure yet. I have to think about it. Maybe actually we'll do half-half, like we'll start half an hour earlier and we'll go on for half an hour longer if that could be okay. But in general, again, I mean, things will be available on video on Moodle if it's really going to be a big problem. Okay. But anyway, I didn't want to interrupt your reflections on whether possibly there are some questions. Are there other questions? Are there actual questions on what we did today? Okay, it doesn't seem so. Then thanks for your attention, and see you next week. And I'll communicate in due course how we're going to arrange it. But let's roughly anticipate 3 sessions next week. Okay, bye-bye.
Bye-bye.
Thank you. Bye.
Bye, see you.